What are some practical applications of refrigeration and heat pump cycles? It's my bet that you can identify most of these nearly immediately, but I want to review with you the true practical real world applications associated with the type of problems you're going to encounter in Chapter 10. So these are practical applications that we observe in our everyday lives associated with refrigeration cycles and heat pump cycles. Gosh, well, here's basic refrigeration systems. Gosh, you probably pass by this unit just about every day in your apartment or where you live. Here's an example of a commercial level, looks like a refrigerator. I'm going to guess that these might be glass doors that people could look at these items. It might be a restaurant level commercial refrigerator. Gosh, here's the frozen food department from Kroger or Food Lion. Gosh, where everything is available by retail. You can go pick it up, but it all stays frozen. Now, what do those three things have in common? Of course, they all have that same schematic in mind, where here's the cold space for all three of those. We're removing heat from the cold space with a refrigeration cycle, block arrow going counterclockwise, and we're rejecting heat up to the surroundings, just out to the room or the commercial space. Well, here's a window air conditioning unit. It's also operating on that refrigeration cycle. Why does it look a little different? Well, it's because what it's doing is that refrigeration cycle is contained within this window unit, and we're bringing in warm return air from your room. So there's a fan in there that's pulling in the air. It's blowing across some cooling coils associated with the refrigeration unit. So the air gets colder, and then, of course, it's blown right back out to you, making you nice and comfortable in your house. And so, where is the heat being rejected? Well, for this window air conditioning unit, heat is being rejected from the back end of this air conditioning unit out to the outside surroundings. So, the refrigeration cycle is contained within this air conditioning unit. And here's a picture of ready kilowatt to remind yourself that, of course, this window air conditioner unit doesn't run on its own. It requires electric power to operate in order to keep you comfortable. Same idea for an automotive air conditioner. Gosh, we take these things for granted so much, don't we? We sit in our car, we quickly turn the engine on so that cool air will blow out of these registers and keep us cool in the cabin of our car. Well, here's a little bit of an overview, and we're going to get into the details of the way this refrigeration cycle works in your car. It's got some basic components, but basically, this little area up here under your dashboard, that's bringing in warm air from the cabin, cooling it down. Air is going across some cooling coils, cooling the air down and keeping you comfortable. How about a heat pump, residential heat pump? Well, what you see outside is this unit out here, okay? And that's what's absorbing the heat. It's actually absorbing heat from the cold outside. So that's what we've got right here, Q.L. Ready kilowatt, of course, is here. We've got to invest some electric power to run our refrigeration unit. And of course, what we're trying to do is transfer heat, which is going to be the sum of the power we're buying. Plus, you can almost think of this as free energy, almost. But the sum of those two is what's going into our house to keep us warm. That's the heat pump cycle. A lot of folks talk about a heat pump by having free energy. And to some extent, that's true, right? Because it doesn't cost us anything to get this form of heat transfer energy combined with this power that we are purchasing to get the sum of those two up into heating our home. One you might not be quite so familiar with is called an industrial chiller. And the purpose of an industrial chiller, and here's a photograph of a chiller that's got the refrigeration cycle components contained in it. We take in a supply of water, basically warm water coming in. Water goes across the cooling coils of the cycle to produce cold water. And so the purpose of an industrial chiller is to provide a cool and steady flow of water to a use point. And in many, many applications of an industrial chiller, we use that cold water for air conditioning. And also in a lesser percentage would be process cooling. And I worked in a manufacturing facility where we use a lot of chilled water in order to cool down other hot liquids that needed to be cooled down in our manufacturing process. But by far and away, industrial chillers are used for air conditioning purposes for large office buildings and other commercial complexes. Here's a little sentimental journey about the way refrigerants have evolved. So, of course, you're going to see that refrigerants are phase change substances. So they're not ideal gases, they're phase change substances. And that's the way you're going to learn how these refrigeration cycles work. So back before the turn of the 20th century, basically ammonia, NH3, was basically the only refrigerant that could be produced that worked, that could power or be used as the working fluid for a refrigeration cycle. And that's the sentimental journey of when my dad was growing up, sort of in the early to mid 20th century. There were some dangers associated with ammonia being used as a refrigerant. And so then, based in myself as a child and then growing up, Freon 12, which was a manufactured, let's say, a polymer liquid fluid, was invented at DuPont. And so Freon 12, when I was a child, was the common and commonly used refrigerant. Later, as I came back to graduate school, R22, refrigerant 22, Freon 22 was a commonly provided refrigerant. And then with some additional inventions and manufacturing and improvements in environmental friendliness, R134A was invented. And this evolution continues on up into today, both to be more environmentally friendly as well as more efficient in terms of phase change behavior. And so there has been an evolution of different refrigerants going from ammonia all up to nowadays R134A and beyond. So you as an engineer are going to be asked to learn how to use the property tables for ammonia, for R22, and R134A. So as we come near the end of this video, imagine life without refrigeration. Just imagine this. So refrigerators in the US only became widely affordable in the 1940s. After World War II, did refrigerators become affordable to most people in the US? So imagine not being able to the grocery store and select refrigerated or frozen items off the shelf. Imagine having to preserve or store your food not in a cave. Imagine having to store your food in a dried or salted environment simply so your food won't spoil. Imagine not having a refrigerator in your house. Air conditioners, they only became widely affordable in the US, I would say in the 1950s, affordable to most working families. They became widely affordable in the 1950s. Imagine coming to work or sitting in your car, driving your car, being in your office place without air conditioning. Imagine what that might be like for you. And also imagine how lucky we are here in the US, because in many countries around the world, neither refrigerators nor air conditioners are really affordable to many people today. So we're really we're fortunate here in the US to be able to afford and access this kind of technology. And so my conclusion from this short video of applications is that our way of life strongly depends on the basic refrigeration cycle or heat pump cycle. It keeps us comfortable, and we really depend on these really as we sort of treat it now as an expectation or almost as an entitlement to living. Very interesting things to think about and reflect on as you get into Chapter 10. I hope that helps you sort of appreciate what we're going to cover in Chapter 10 regarding vapor compression, refrigeration cycles, and how they affect our everyday lives.